14 green ones. So you cannot answer that question until you calculate both the average and the standard deviation. So how do you calculate the average from this problem? Okay, so the mean is n times p. And what's n? 90. There's 90 total M&Ms. And what's p? 10% chance of getting a green. So 10% of them are green. So I expect to have how many greens? 9 of them. So by itself, that's not enough information. Is 14 far enough away from 9? I don't know yet. I don't know what sets up distance. So what is the standard deviation going to be? Square root of NPQ. Where do you get that 0.9 from? What the hell is that?
1 minus the probability.
Yeah. If 10% are green, what percent are not green? 90%. Remember, P and Q are opposites. P success here is green. Q must be not green. I failed at getting a green, right? I think it's 0.9. Is that 0.9? Is it 8.1? Well, 9 times 0.9 is 8.1. So 90 times 81, 8.1. Screw rid of that 2 point something. So what's the maximum expected value? Do I really have to look at the min expected value here, truly? Only if they ask you to do both. Why am I only going to look at the max? Because 14 is above 9. I want to see how far up can I go and still be usual. So what is mean plus 2 steps? What's 9 plus 2 of these? 14.7. So is this unusual? No, it's within the expected amount, right? It's not unusual? Oh, I'll do that to you. Is that cool? What would the minimum be just to do it? The minimum would be mu minus 2 sigma, so that'd be 9 minus twice this.
3.3.
Yeah, 3.3, yeah. So I can expect anywhere between almost 3 and almost 15, right? Just to kind of round them up to whole numbers. So if I open a pack of 90 M&Ms and I saw 30 green ones, that's unusual. Something happened that day in the M&M factory, right? The little green thing got stuck open. Oh my God. Not sure why that would be bad, but okay. Okay, so that's really the worst that homework is going to look like in section 5.4. It's a very nice little section. Just wants to set up the mean and standard deviation and have you work with it a little bit to get used to it. So here we go. We are getting into the most important chapter of the semester. Chapter 6. And I've got a little bit of a handout. Let me see. That's going to be a neat part of the... Are you going? Hey, you're going. Sweet. All right. Got to give you another minute. So guys, what did we learn last time about probability and area? If I graph a probability distribution, how do those two things relate?
The area is equal to probability.
Yes. Area equals probability if I graph the probabilities, right? So here's an idea with that. On a dartboard, if I'm a bad player and I just randomly start tossing darts up here, is it more likely I'll hit the bullseye or that I'll hit somewhere out here? Because this area is so small. Cool, right? I suck at darts, so that would basically be a random toss if I threw it out there. Right? So it should be the truth that area matches up with, and we actually already know that. Remind me, within one step, within one standard deviation of the mean, what percentage is there for normal? And why is there more than half in there? Because that's where most of the area is, right? So that makes sense. So why, with the empirical rule, it's nice, but it also is very weak. Because can you tell me how much is between 1.11 and 2.57? What area is that? I have no freaking clue, right? I could estimate it maybe if I drew a perfect normal curve and try to see what percentage is in there. Screw that. So thank God that somebody made a little chart for us with all the probabilities that go on. I basically call it empirical rule on steroids, right? So it just, empirical rule is 1, 2, 3. The chart is everything in between, at least out to 2 decimal places. So let's familiarize ourselves with this chart. And actually, that's what I was trying to sneak in here for. How many of you guys anybody not brought your book today? You're going to want to cycle up next to somebody who did, possibly. Or I think I'm going to try to throw it up here too. Oh, man. Whoever's in this class before me, I love them. Okay. All right. By the way, guys, I'm going to show you something that I keep forgetting to show you. I think they make reference to this in your book. But there's a website that's got some nifty resources, given that your internet works.
There used to be Wi-Fi in this building. Did they shut it off for a particular reason, or?
Probably something related to budget, I'm sure. Well, you can't blame them. By the way, guys, don't make any long-term plans based on next summer taking courses.
Summer won't be here?
Next summer will probably not be here. We had to cut we cut 50% of the courses, then we cut like another 20%, and then just recently we had to cut another 50% on top of that. So we have like one section of Math 90 to Math 180 or something. I mean, just one of each. This summer's going to suck.
I had to go to Palomar to get classes.
All right, so.
Isn't that everywhere?
More than likely, yeah. So guys, if you go to Google, type in Triola Statistics Series. There's a companion website. Click on our book. And it's got, for example, the only thing I want from here right now is the formula card. So I can actually click this and it gives a PDF formula card so I can print out copies of it. It's got TI-83 helps with your calculations in your calculator, student supplements, blah, blah, blah. What's the matter? All right, someday this is going to come up. So what we're going to see is what you'll see if you go to the very, 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 very back of your book, the inside part of your book in the back. Notice how this chart is set up. This chart has z-scores on the very outside. Here we go. How do I... Where's that? I don't want that there. Oh my God. Screw it. All right. So for example, You see the z-scores up here. So if you want to look up, let's verify. The first thing I want to do with this is let's verify the empirical rule is on here. Because we all have learned the empirical, we know it. This thing better not tell me any different numbers or else we're going to screw this thing, throw it out. So what do we know has got to be true about normal curve, what we just said, between 1.00 and negative 1.00, it's got to be 68%. Now what does this chart do? Whenever I look up a z-score, the number it gives me is the area below that z-score. You guys see that? I'm going to say that approximately 900 more times because people forget that for some reason. This chart, all it does is when I look up a z-score, the number it gives me is the area below what I just looked up. So if I'm doing a problem and I want the area above that, that's not my answer. I got to do something to it, right? So this chart's very single-minded. So if I want to look up the area below 1.00, I want this area here. First thing you get used to is how this thing works. These up here are the second decimal place. I wish I knew how to shut this thing down. Oh. So if I want 1.00, I go 1.00. So that would be right here. So if I wanted, for example, 1.07, I go 1.07, that's what it would be right there. That's the area below that z-score. So it makes sense that all of these areas are bigger than 50% because the mean cuts it in half. And the minute I get above the mean, I've got more than half below me, right? So by the time I get up to one step, what area is all this? 0.8413. Do you guys see how to read that? Now, how do I get negative 1.00? I go back to the negative table, right?
0.1587.
Beautiful. So you go back to negative 1.00 is this first guy here, right? So that's the area that's below this. So what area is in here then from my table, that these numbers I got? How do I get the area inside? Beautiful, because this is too much. It's supposed to stop right here. This doesn't stop. If I subtract that much, that'll be what's in between, right? Physically, that makes sense. So what is 0.8413 minus 0.1587? $1,587. 6826, right? Which is basically 68%, rounded to a whole number. You guys with me? So when I first talked about empirical rule, I did say that they were still approximations, but they were a lot more exact than Chebyshev. Chebyshev had that at least built in. Empirical is exactly, given that they were rounded to 68, it's still 68.26. That's pretty damn close, right? So obviously right now I'm just trying to get you used to how to use the chart. Now we're going to get into specific problems. Where the hell would this help me, right? So here's kind of a silly example. IQ scores. And IQ scores get overused for this kind of problem, but oh well. IQ scores are known to be normally distributed. If you know your IQ score, you can actually figure out how you are relative to everybody else in America because the mean is 100. I don't know if you guys remember Forrest Gump. He had like a 70 or something. So there's a certain level below which you get to go to a special school or not, right? So mean is 100. The standard deviation is 15. Membership in something called Mensa. Have you guys ever heard of Mensa?
Yes.
Membership in Mensa requires greater than 133. I think from what I can't remember now. So I want to know, so these are normally distributed, right? And I couldn't even use this chart if it wasn't normal. So a big chunk of this class is all about, okay, when is something normal enough to use the chart? Right? So right now they're going to have to tell me it's normal. So this we know is normal. I want to know the probability that somebody has higher than 133 IQ. To see, what percentage of people